So this is chapter 11. We're not going to talk about energy anymore. Now we're doing something completely different. This is impulse and momentum. So totally new topics. So we are still talking about interactions, though. So here are the learning objectives. To understand interactions from the new perspective of impulse and momentum, to learn what is meant by an isolated system. I thought we already talked about that in a previous chapter on energy, but whatever. To apply conservation of momentum in simple situations. This is probably the most important section of this entire chapter. This is super important. Now I remember. And we're going to understand the basic ideas of inelastic collisions, explosions, and recoil. So I used to work at a place called Fermilab. So this is in west of Chicago in Illinois. This is 4 miles in circumference. So basically you get protons smashing against protons or antiprotons. And so it's particle physics. And when I used to do particle physics, guess what I used to use? Not just me, but particle physicists use all the time. Conservation of momentum. Super important in particle physics. Okay, so what we want to do again, we want to talk about collisions, right? Or interactions, collisions, interactions. And what we want to know, what we want to know, I should say want, I guess. We want to know the velocity before a collision or the velocity after a collision. So that's what we're interested in. So in other words, if we know this, we want to know that. If we know that, we want to know that. So that's what it is. Okay, so here is a collision. So you can imagine a tennis ball moving, and then something happens, right? There's a collision. So here's a silly question. Why does the velocity of the tennis ball change? Well, obviously because the racket exerted a force on it. Now, is the force that the racket exerts on a ball, is that force constant? No, it is not constant. All right? Ooh. So the force is not constant. Also, how long, so you have a racket interacting with a ball. Is that interaction instantaneous, or does it take a while? Well, it doesn't take very long, but it's certainly not instantaneous. Okay, so in other words, like I could say, how long do the racket and the ball interact? Well, I don't know, but it's not instantaneous. Okay, so just summarize. Force is not constant. That means acceleration is not constant. The interaction time is not instantaneous. Okay, ever heard of a gooseball? Well, here you have a gooseball. And that's the correct spelling. So the gooseball colliding with the floor. So here it's coming down, just touching the floor. And so this is time lapse, right? And so you can see what happens to the gooseball. And then it sort of kind of rebounds. All right? So that's the gooseball interacting with the floor. So the force that the floor exerts on the gooseball, or the force that the gooseball exerts on the floor, is it constant? I don't think so. Certainly not. Is the collision instantaneous? No. All right. Okay, here's a graph. So this is what we have. This is a setup from lab. This is aluminum track. This is a force sensor. It's attached to the track, so this thing doesn't move. Here's a cart. Yeah, the magnet. And so they're both same pole, so they're going to repel. So this moves down here. They're going to, right? The magnets repel, so it gets to a certain point, then it bounces back. Okay, so here's a force plotted there, time plotted there. So is the force constant? Obviously not, right? It's pretty much zero, then it gets high, then it gets to zero again. Is it instantaneous? Certainly not. This is 6.1 seconds, this is 6.2 seconds. Okay, so there you go. All right, so I've discussed 3 interactions. Now think of any collision you want to. If you're careful enough, do all collisions vary with time? Yeah, right? They sure do. If you look close enough, they certainly do. Okay, now, and if the force varies with time, that means that the acceleration varies with time. And if the acceleration varies with time, it's not constant. Very good, right? If the acceleration is not constant, are we able to use the kinematic equations to describe the problem? Absolutely not. Remember, we only can use kinematic equations for constant acceleration. Okay, so wow, we can't use kinematic equations. What are we going to do now? Well, that's what we're going to discuss. All right, so we can't use kinematic equations. So we're going to use something called the impulse momentum principle. And it's kind of long, but whatever. And I'm going to show you the derivation because it's short and it's nice to see. Okay, so start off with the most important equation in all of classical physics, F equals ma. So we have the force. Now remember, the force varies with time. So I'm going to do this on purpose. So what I mean by that is force is a function of time, right? Force depends on time. So I want to do that just to emphasize that the force is not constant. Okay, so force equals ma. And again, if the force varies with time, the acceleration varies with time. Now, and yeah, we're going to assume constant mass. So what's a? It's dv dt. So I'm going to write dv dt, right? Okay. Now, that's just good old, all right. So now I'm going to multiply both sides by dt. That's okay, I can do that. Multiply both sides by dt. So I have f as a function of time times dt equals m dv as a function of time. Okay, now, when you have something like that, what is this equation asking for? Please integrate me, right? I mean, that's what, come on, integrate me. So let's integrate both sides, right? If you do something to one side, you got to do it the other side. So integrate both sides. Now, this here is called impulse. And they use J, uppercase J. They can't use uppercase I because everybody uses that for electrical current. So they got to use J, right? IJ, or what's next, whatever. Okay, so what is that? What is an integral? It's the area under the curve, right? So if you have a force versus time curve, how about that, right? Force versus time curve, the integral is just the area under the curve. So in other words, the impulse is just this area. And the computer can calculate that for you, right? Here it says the area is 0.49 whatever Newton seconds, right? Because the force is Newton, time is seconds. Right? Newton seconds. So impulse is in Newton seconds. Okay, so this is, all right, so impulse, so it's the area under the F versus T graph. Come on. All right. Now, this here is also, it's also equal to some average force times delta T. Okay, so this is also equal to some average force times some delta T. So in other words, we could figure out some average force, multiply it by this delta T, and it would equal the area under the curve. All right? Okay, so there you go. So integral f dt, that's called the impulse. This is the area under the curve, no kidding. But this here is also equal to this. That's important. Okay, now let's work on over here. Let's work at this. Okay, so what's the integral dx? X. So what's the integral of dv? V, but we're going from some initial time to a final time, right? Right? So it's just mv final minus mv initial. And remember, that's what we were interested in, right? We want to know either the final velocity or the initial velocity, right? Okay, now, if you've ever taken a physics class, you should recognize that. Momentum, little lowercase p, momentum, lowercase p is mv. It's really a vector. I guess I should, all right. So this is just p final minus p initial, which is just delta p. Okay? Now this is really all vectors, sorry. Okay? So therefore, you know, if you really want to, yeah, vector, right? Vector, all right? You can say that J equals delta P, right? You can say that, which is also equal to F average delta T. So, you know, I mean, there's a lot of ways of writing this impulse momentum principle, you know. I mean, that's what it is, but you have to understand that that equals that, right? So, you know, that's what I mean. There's a lot of ways of writing it. You know, you just write whatever you need for your particular problem. But that's it, all right? That's called the impulse momentum principle. Some people call it the impulse momentum theorem, whatever you want to call it. All right, so there it is. Yay! The impulse momentum principle. J equals integral f dt, which is f average delta t, which is delta p, where p is mv. You probably heard that before, right? If you see a big truck going down a big hill and it's going really, really fast, you say, wow, that truck has a lot of momentum because it has a lot of mass and a lot of velocity. So that's what momentum is, mass times velocity. Super incredibly important, momentum. And again, J is the area under the curve. Okay, so here's the deal. All right, so according to F equals ma, which equals m dv dt, what causes a change in the velocity of an object? Well, obviously, force, right? I mean, if there's a delta v, which is a change in velocity, there has to be a force. So force, right? So we learned that a long time ago. That's nothing new. But now we're looking at it from a different perspective. Now we're saying, according to the impulse momentum principle, J equals delta P, what causes a change in the momentum? Well, the impulse, right? If this is not equal to 0, that can't be equal to, that's not equal to 0 either, you know? So the impulse causes a change in momentum. And remember, impulse, time varying force times a time, right? So this is like an interaction or a collision that is not instantaneous and the force is not constant. And you can also think of it like that or like that. All right? And again, why do we have to make a mountain out of a molehill? Why do we have to, what's wrong with just doing this? Why do we have to do this? Well, we have to do this because the force is not constant. So we can't use kinematics. All right? Okay, so here is the plan. We want to know the velocity of an object either before or after the collision. We can't use kinematics for the collision, right? We can use it before and after the collision, but we can't use kinematics for the collision because the forces aren't constant. That's okay, not a big deal. We don't have to know all of the details of the force. All we have to do is be able to somehow measure the force as a function of time. If we can do that, we're done, okay? We're done, because then we can just use our good old friend, right? In other words, if we can measure the force as a function of time, which is a piece of cake, you know, with a force sensor, and then calculate the area of the curve, bingo, we're done, right? You know, for example, if we know this, if you can calculate this, and you know this, then you can get that. If you know this, and you know that, you can get that. I mean, either way, right? Either way. So that's what we want to do. Okay, I'm going to give you a challenging question right now, all right? And I gave you a few hints. Okay, so this is a really important question. This is like the key concept here, okay? And you're going to use that. But let me just give you just a few more hints. So well, maybe I won't. No, I'm not going to. You just figure it out yourself. We'll discuss it later. Okay, so please pause your video and use this. And don't forget delta P is this, all right? And figure it out. Thank you. Okay. Maybe we just leave it. All right, so we're back, and I hope you figured it out. So, but we have to make a few approximations. I was going to tell you that before, but I decided not to. So, you know, we have this paratrooper way up high, right? And she has, so here's the snow, and here's the dry ground or bare ground. Now, we're going to assume that the initial momentum is the same for each situation, okay? And that's not exactly true, right? Because come on, I mean, maybe the snow's 10 feet high or something like that, you know? So this momentum here is not going to be exactly the same as the momentum right here, but it's going to be really, really close, okay? So the assumption is that the P initials are the same. And again, that's a really, really good assumption. Now, what's the P final? Well, the P final is 0, right? The person stops. So that's not an assumption, that's just a fact. So P final equals 0. All right? So if P initials are the same and P finals are the same, then what can we say? Well, if the P initial is the same and the P final is the same, the delta P is the same. That means that the impulse is the same. Well, that doesn't help. This was what helps. Okay, so what we're going to say then, okay, so we're saying that the J's are the same, right? The delta P's are the same, the J's are the same, so the F average delta T is the same. Okay, but what's the difference though? What's the difference between, you know, landing on bare ground or landing on snow? What's the difference? Well, when you land on, here, let me just write something. So F average delta T snow equals F average delta T, what did I say? Bare ground. All right, what's the difference? Well, you know, when you land on dry ground or bare ground, how long is the collision? Real fast, right? Bang. When you land on a big pile of snow, how long is the collision? Well, it's going to take longer, right? It's going to slow it down. Okay, what we're saying is that for snow, delta T is kind of, I'm going to say big, right? You know, maybe 2 seconds, right? Whereas for bare ground, delta T is really, really short, right? Like almost instantaneous. But this has to equal that. So therefore, this force has to be bigger than that force, right? Okay, again, because the products are the same. So therefore, if she lands on the bare ground, there's going to be a huge force. She's going to die. On the other hand, if she lands on the snow, the force is not going to be so great, and maybe she'll live. Okay? But, all right, so that's it. So, let's answer the question. So, does the presence of snow change? So, does it change to change momentum? Absolutely not. We already talked about that. Does it change the paratrooper's impulse? Absolutely not, because the impulse is to change momentum. Does it change the force? Yes, because the impulse equals F delta T. And the thing is that the delta T's are different, right? And so the forces are different. Make sure you understand this. This is like this is the essence of the impulse momentum principle, you know? So that's the thing, you know? So if you're ever a paratrooper and you have a chute that fails, don't ask me, but somehow you want to land on something that will make your collision take a long time. So, you know, try to fall in a bush or something, I don't know. But anyway, you just want to have a long time, because then the force will be small, as opposed to landing on bare ground. Okay, so let me emphasize this. So this is 1904, St. Louis. This is the pole vault, you know, track and field, the pole vault competition. And these poor crazy people, they just had like sawdust or something like that to land on. And why did they use sawdust? Well, you know, to increase the delta T a little bit, but did it really increase it by much? Not really. Not really at all, but luckily they didn't know anything about fiberglass poles, so they couldn't pole vault very high. Thank goodness, right? But okay. So nowadays, look at that. So nowadays, like the world record is over 20 feet, and they don't land on sawdust anymore because that would not be fun, right? Landing 20 feet on sawdust. So they have these gigantic, thick pole vault pits. And, you know, what do? They just slow down the collision, right? So the collision takes a long, long time. So if this is really, really big, what's the average force going to be? Really, really small. And they use, you know, they also use pits for like high jump and things like that. And it's just impulse momentum. So whoever understood impulse momentum probably designed pole vault pits, huh? Okay, very good. Okay. All right, so let's keep going. So let's drop a ball. So pretend I drop a ball. So there's a ball, right? So let's explain what we would observe in terms of Newton's laws and forces. Okay, so you drop a ball. So why does it fall? Because the Earth is exerting a gravitational force on the ball, right? Well, F equals ma, so that means the ball's speed is going to increase. Now, eventually the ball is going to hit the ground. And the ground is going to exert an upward force on the ball. And the force is not going to be constant. I mean, when the ball is just barely touching the ground, there's not very much force. But you know, shortly thereafter, there's going to be a larger force. So really, you know, you have a time-varying force, right? That's caused by gravity, okay? And of course, and that's going to change the direction. It's going to accelerate, right? It's going to accelerate. Speed is going to change. Direction is going to change. And then when the ball is up in the air again, it's free fall, right? And so again, gravity is still exerting a force this way, so it's going to slow down. Okay, not a big deal, right? That's not a big surprise. But now let's talk about this in terms of impulse. Okay? Impulse. Okay, so here's the ball, you know, then hits the ground and it rebounds. So how many impulses act on the ball for the entire, you know, from this point to that point? How many impulses act on the ball? Well, here's one, right? From here before it hits the floor. Here's another one. After it leaves the floor, goes up. So there's two, right? But how about here? You know, gravity's pulling it down. Normal force is pushing it up, right? Okay, so there you go. All right. So 1, 2, 3, 4. Okay. All right. Here's a question. So now we're not no approximations. We're being very, very careful. Is the normal force that the floor exerts on a ball, is it constant? For the entire collision, is the normal force constant? So pause your video and figure it out. Okay, we're back. No, it certainly isn't, you know, because again, you know, the collision takes time. At first, the ball is hardly touching the floor at all, you know. Okay. So the normal force is not constant. We've never talked about that before, right? We've always assumed it's constant. Okay, how does the maximum normal force on the ball compare to the ball's weight? Yeah, just magnitude. So just think of what happens, right? Right? So how does the maximum normal force compare to the ball's weight? So pause your video and figure it out. Okay, so what happens? The ball hits the floor, then it goes back up. So doesn't that mean that the normal force has to be greater than the weight? Sorry, the maximum normal force doesn't have to be greater than the weight? Yeah. Okay? And I just explained why. All right. That's a good place to quit.